Today we are going to be multiplying and dividing radical expressions. So we'll look at the directions here. It tells us to simplify. And all variables represent non-negative numbers. Now, in all the problems that we have here, we actually don't have any variables with the regular number problems, but you do see some variables here. And basically all this means is that we can't have a negative number underneath the radical sign, because as we learned before in regular Algebra 1, that we can't have a number that's negative underneath the radical sign, to be a real number, that is. However, in later courses we'll see that we have another number system called imaginary numbers, and we can end up coming up with a negative 1 representing the square root of that equaling I. But for right now, we'll just go with what we know, where we do not have negative numbers underneath the radical sign. So on this problem, what we're going to do is treat this as a fraction and then multiply these two terms. So when we're multiplying, a rule is that we can take those two numbers, the 5 and the 2, write them underneath the same radical sign and multiply them. Down below we have that square root of 11. Well, 5 times 2 just makes 10. But this is not simplified because of the radical in the denominator. And we want to do something called rationalize the denominator, which we talked about before. So what we're going to do is we're going to multiply by 1, because 1 doesn't change the number. However, we can write 1 many different ways. One of those ways is the square root of 11 over the square root of 11. And what that will do is it will multiply. The 11 times 11 will make a perfect square. And so now what we have is this. We multiply the 10 and the 11, we get 110. Down below we get 121. Well, we could take that square root of 121, and we know that is just 11. So this is the simplified form. The square root of 121 over 11. I'm sorry, not 121, but the square root of 110 over 11. On this next one, it's a division problem. So we can't multiply the 3 and the 5 because the 3 is not underneath the radical sign. However, we can reduce this. So you see how 3 and 15 have a common factor of 3. So we reduce it and we get a 1 over 5. So now we've made the problem a little bit simpler. We can also do this. You see how 8 has some factors. And we're always looking for factors of 4, 9, 16, 25. The reason I look at these is because these are perfect squares. See, 4 is a perfect square. I can simplify that 8, that square root of 8, down to something smaller and easier to deal with. So now, once I've kind of done some reducing, I've got this, the square root of 5 over 5 times 2 square roots of 2. See, 5 times 2 because I brought down this 5 here, and then the square root of 4 is 2. So that's where that came from. Now I want to rationalize the denominator. So I'm going to multiply by the square root of 2 over the square root of 2. And so I'll go ahead and do that work, and this is what's left over. The square root of 10 on top, because 2 times 5 makes 10. Down below, I'll multiply those two numbers. I get 10, and then the square root of 2 times the square root of 2, well, that makes the square root of 4. Well, I go ahead and take that square root, and that gives me 2. So now I have 10 times 2 on the bottom of the fraction. So my final answer is the square root of 10 over 20. And that's my answer. Now, I don't want to do any reducing because the 20 is not underneath the radical sign. Looking at our next one here. Now, we can't do any dividing of 2 into 8 because we've got to add the square root of 32. But what we can do is this. I can treat this as two separate terms. 8 over 2 plus the square root of 32 over 2. Now, the square root of 32, I can't divide 2 into that number because the 32 is underneath the radical sign. However, I can take out a perfect square. You see, 16 is a factor of 32. 16 times 2 makes 32. So I could rewrite this way. 8 over 2 plus the square root of 16 times the square root of 2 over 2. And now I'll be able to do some reducing. So the square root of 16 is 4. So now I have this, 8 over 2 plus 4 square roots of 2 over 2. Now I can do the reducing of 2. So I couldn't do it until I could get both of them to be able to divide by 2. So now I can. 2 goes into 8 4 times. 2 goes into the 4 2 times. So here's my answer. It's 4 plus 2 square roots of 2. And that is my answer. Next one here, I'm going to use that FOIL method. So first outer, inner, last. Square root of 2 times the square root of 2 makes the square root of 4. Those are the first terms. Now I do these. So I do 3 square roots of 2. And then I do the inside terms. Negative 4 times the square root of 2. And then I do the negative 4 times 3 makes negative 12. And so from that point, all I'm going to do is collect like terms. So the square root of 4 is 2, and I'll combine it with this negative 12. See, these are like terms here. Negative 12 and the square root of 4, I can combine together. And then the same thing over here. 3 square roots of 2 minus 4 square roots of 2. So go ahead and do some work there. It makes negative 10. 2 minus 12 makes 10, but it's negative. And then minus the square root of 2. Now minus the square root of 2 because 3 minus 4 makes 1. So you can even write it as negative 1 times the square root of 2. So either way will work. Looking at our next one, we got to multiply the square root of 3 by both of these terms. So we go ahead and do that. Now I can do the first one here, 4 square roots of 3. But this next one, before I do that, you see how I have a perfect square in 18. See, I always think about those perfect squares as I'm dealing with them because I want to reduce it. See, 9 times 2 makes 18, and I can reduce that to make it easier to deal with. See, the square root of 9 is just 3. So now I have this. I got plus 3, and that came from the square root of 9. And then 3 times 2 makes the square root of 6. And that would be my answer right there. And I cannot combine them because the radicands are different. Over here, same sort of thing. See, this is a perfect square. It makes 7. Square root of 49 made the 7. The square root of 27, well, there is no perfect square. Well, 27 is not a perfect square, but there is a perfect square in 27. You see, the square root of 9 is 3. So I can rewrite that as plus 3 over the square root of 3. Now, square root of 5, that's a radical that cannot reduce. So what we're going to want to do is rationalize that. So we're going to multiply this by the square root of 5 over the square root of 5. And so when I do that, I multiply both terms by that square root of 5. So I'm left with a 7 square root of 5, and then plus 3 square roots of 15. And then down below that, well, the square root of 5 and the square root of 5 make the square root of 25, which just makes 5. And that would be my answer right there. Well, let's take a look at these other two types of problems. We've got this one that talks about electrical current in amps can be represented by the square root of W over the square root of R, where W is power in watts, and R is resistance in ohms. How much current is running through a freezer that has 150 watts and 25 ohms? And so what we're going to end up doing is just substituting. This is the number of watts, so we're going to take that number and put it right here in place of W. Then we're going to take the 25 and put that in place of R. And so now we've got this, 1050 over the square root of 25. Well, we can divide 25 into this number. It goes in there because, you see, 25 goes into any number that ends in double zeros, 25, 50, which this one is, or 75. So how many quarters make $10.50? Well, 4 quarters make $1, and so 4 times 10 makes 40. And then plus the 2 quarters that make 50 cents, that would be 42. So I know that 25 goes into 1,050 42 times. So I've got the square root of 42. Well, we want to know what that represents. Well, we know that the square root of 49 is 7. The square root of 36 is 6. And so what I can do is I can look to see which one it's closer to. See, 49 from 42, that is 7 numbers apart. 36 from 42 is only 6 numbers apart. So it's right in the middle, pretty close to 6.5, but just a little bit closer to 6. So maybe like 6.48 or so. And so I would just do a little approximate sign. So the little squiggly equal sign just means about 6.48 amps. Now where did I get amps from? Well, that's what it is, electrical current in amps. And so when I divide watts by ohms, you get amps. Next one, the period of a pendulum is the amount of time it takes one complete swing to return to its original spot. So here's my pendulum, and so I should probably draw like a little ball right here showing that it's swinging. So let's say it swings this way, and then it stops, and then it swings back. And so it's that amount of time that it takes it to get to here and then back to its original spot. And so the period, which is the time it takes for it to do this, can be represented by this formula, where L is the length of the pendulum in feet, Well, here it says find the period, which is the time it takes to do this, if the pendulum is 5 feet long. Well, that's what we're going to do, is put that 5 right in for that L there. So I got 2 pi times by the square root of 5 over the square root of 32. And so all I'm going to do is simplify this a little bit, because this seems really complicated to do the work here. And so if I want to do this without a calculator, this is where simplifying comes into play. So I know 32 has a factor of 16. So what I'm going to do is I'm going to do 2 pi times the square root of 5 times the square root of 16 times the square root of 2. See, just broke that 32 down to two numbers that one of them is a perfect square. So this makes 4 now. So let's rewrite this. Got 2 pi square root of 5 over 4 square roots of 2. Well, I could do some reducing now. I could take out that 4 and reduce it down to a 2. And so now I've got this. I've got pi, and then I've got the square root of 5 over, and then I've got 2 square roots of 2. Well, let's get rid of that square root of 2. I want only one radical. I don't want 2. And so I'm going to go ahead and multiply this by the square root of 2 over the square root of 2. And so when I do that, I end up with this pi square roots of 10 over, and then this makes 2 times 2. You see, square root of 2 and square root of 2 make the square root of 4. Square root of 4 equals 2, so that's where I got the 2 times 2. So now I've got this, pi square root of 10 over 4, and that's the time it takes. Well, I want to know what that represents, so let's go ahead and figure out what that is about. Well, I know pi is going to be 3.14. Now, what's the square root of 10? Well, the square root of 9 is 3. The square root of 16 is 4. So I know that 10, the square root of 10, is going to be pretty close to 3. But it's going to be just a little bit bigger, maybe like 3.1 or so. And then I'm dividing by 4. Well, if I go ahead and do some work, let's go ahead and just round this stuff a little bit easier here. So I'm going to, instead of 3.14, I'm just going to do 3.1 times 3.1. And it's just going to give me an about approximation of what this is. So I do that work, I get 3, and actually first I get 1, and then I get 3, carry a 0, and then I end up with a 3 and a 9. And so I go ahead and add that stuff together, I get 9.61. So about 9.61, and now I just need to divide that by 4. So 4 into that 9.61. Well, 4 goes into the 9 2 times, and then it goes into 16 exactly 4 times, and then we've got this 1 left over, so it's going to be 0, and then it's going to continue. So I'm just approximating it, so I'd say about 2.4, and then the time it takes is in what type of units? Is it in seconds? Let's see here. The period of a pendulum is the amount of time it takes to make one complete swing, and it doesn't say, so I'm just going to go with seconds here. So I'm pretty sure that's what it is, since I didn't specify that in the problem, so I'll just write that down. So 2.4 seconds is just an about approximation, and I was able to do that without a calculator. All right, those are the types of problems you'll see on tonight's homework. Good luck.